15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello once again. Thank you for joining us on the Space Nuts podcast. Andrew Dunkley here with our good friend, Professor Fred Watson, astronomer at large. Hello, Fred.
Hi, Andrew. How are you doing? I'm honoured to be your good friend.
No, I'm honoured that you are my good friend. No, it's good to see you again. Hope you're well.
Yep, all good.
Excellent. Now, on today's program, we are going to be looking at lots of stuff, which is what we do on the Space Nuts podcast, astronomy, space science and stuff. We're going to talk about your little trip down to Adelaide shortly, which is very exciting. There's something happening down there. We're going to find out about the magnetic fields of M87, the black hole, and another echo from the exo-asteroid known as Borisov, which we talked about only recently, but this was the second such exo-asteroid that passed through. Of course, the space doogie was the first, Oumuamua, which is no longer a doogie, it's a cowpad. But we explained that last week. Some audience questions as well about whether or not other planets have magnetic poles. Now, I've never even considered the possibility. So there you have it. We'll look into that and how to photograph distant objects, photon rates, whether or not dogs and cats can live together in harmony. We're going to cover it all this week on the Space Nuts podcast. But first, Fred, let's talk about your little sojourn to the city of Adelaide, the city of churches in South Australia. Yep. Where there is going to be the Australian Space Discovery Centre. Is it officially opened yet, or is it still in the? It is, isn't it?
No.
No.
Okay. So it was launched. It's
launched.
It's a space thing, so it was launched. But in fact, it's not open to the public for about another month, a little bit more. They're test running it with, I think, booked groups and things of that sort, just to make sure everything works out all right and all the displays they all hold up because the public. With all due respect, the public can be quite rough on exhibition things. It's a tough gig for an exhibitor. But the story is that, first of all, the story starts with the Australian Space Agency, which came into being a bit more than, I think it's 2 years ago now. But they got their headquarters, which are in Adelaide. About a year ago, they moved into what used to be a hospital. And it's a repurposed building. It's called Lot 14. It has lots of high-tech organisations within it, including the Australian Space Agency, which set up shop there, as I said, about a year ago. My connection is kind of twofold, but it's basically because the government department I work for also overlooks the Space Agency. It's part and parcel of the same. It's the same ministerial portfolio. I know for the past year or so that I've been involved with this, they've been planning an exhibition, a public exhibition, the Space Discovery Centre, to showcase Australia's place in space, advertise the way Australian industry contributes to space, including the Moon to Mars program that NASA has. They're part and parcel of that. And also to let people know just how much space activities affect their day-to-day lives. Nearly everything we do has got a space connection, usually through communications satellites or weather satellites or resources satellites, the whole deal. So many people don't realise that, and that's really the focus of the exhibition. The exhibition was essentially set up under contract by Questar. I beg your pardon, by Questacon. Sorry, Questacon. Which is the National Science Centre. Questar is what a make of telescope. From a long time ago. Questacon, that's the National Science Centre, and they took responsibility for building the exhibits. Questacon is also part of the same government department that I'm in, so it's a little bit incestuous, but it all worked very well. And my involvement was via Questacon because we had a working group to look at the kind of exhibits that you might put together which would convey the issue of space ethics. It's all about the ethics of spaceflight, whether we should explore Mars, whether we should put satellite constellations up. All of these things are ethical issues which are focused on in the exhibition. So I had a bit of an input to that, along with a number of other people who are far more perhaps professionally involved with ethical issues than I am. My interest is more of a hobby. So that was my contribution. So I got an invite to the VIP preview on Tuesday night, and that was my first trip out of New South Wales in more than a year, and the first time I've been on a plane for more than a year. It was an interesting experience, but to be honest, being on the aircraft itself was just the same as it always was, except we all had face masks on.
Yep.
Yeah, it's quite hard to drink your Qantas coffee with a face mask on, but they let you take it off.
Yeah. So is the Australian Space Discovery Centre a permanent facility?
Yes, it is. It is.
But it'll have evolving and changing exhibitions within.
Yeah.
Right. So it's like an art gallery for space.
A little bit like that, and in fact, that's a really good point, because I happen to know through Marnie, in fact, the new manager of this space centre, a guy is a young man, Brennan Dew, his name is, and he's a really interesting character. And he used to work for Marnie when Marnie was running the Sydney Observatory. And he's now scored this job, and we talked about getting exhibits in, and I'm a little bit interested because, I draw cartoons, which I've been doing for the new book. Some of them are space related. It'd be lovely to have some of my cartoons in the exhibition. It is permanent but evolving. The one thing I didn't mention was that the day after the preview, so this is yesterday now, the Prime Minister actually opened it to great fanfare. So that had a high profile. But there is a travelling version of it, Andrew, which is going all around Australia. So and Questacon are looking after that. And I bet you anything it comes to Dubbo fairly early in the proceedings.
Well, Questacon has been here multiple times over the years, and we used to take the kids to the showground to get involved in some of the experiments and hijinks that they got up to. And we did actually take the kids to the Questacon facility in Canberra once, and went around and experienced some of those amazing things that they have on show there. The earthquake machine, I really enjoyed that. And I'm pleased to say that Judy and I will be in Adelaide in September, October. So we're going to go and
you can go and see.
Definitely have a look at this.
Yeah, go and have a look. You'll love it. You will absolutely love it.
Yeah. Oh, I know I will. I didn't get to go to the one in Hong Kong. They've got a space centre there, but it was closed the day we planned to see it. So, or wasn't open until 1 p.m. and we had to catch a flight to Sydney. So missed out on that one. So, yeah, I'm really excited to be able to go down there. So it sounds like it's going to be a terrific place.
Yep.
So all credit to the department and that beeping's the dishwasher. Sorry.
Okay, that's all right. So just a word to all you Aussie space nuts. You're going to be able to go and see this, and when the time comes, make sure you go and catch up with it.
Most definitely. All right. It's called the Australian Space Discovery Centre in Adelaide. All right, moving on, Fred. Let's talk about our first interstellar story, if you like. And this is a focus on magnetic fields of the M87 black hole. The Event Horizon Telescope has been keeping a beady eye on this.
Indeed, that's right. I suspect these are actually observations that were made round about the same time as the black hole picture was constructed. I'm not clear. I haven't, in fact, read the paper yet. I've got a link to it, but I haven't read it. I'm not clear whether these are more recent observations. But remember the Event Horizon Telescope? It's this conglomeration of 8 different high-frequency radio observatories, which are all in the Western Hemisphere. And so they're all looking at the same part of the sky, and they made these incredible observations of M87, the galaxy about 55 million light years away. It's a galaxy with probably the biggest central supermassive black hole of any galaxy in our vicinity. So it's the nearest super duper black hole, which is why they chose that, because the bigger the black hole is, the bigger the event horizon is. And actually, M87's black hole's event horizon is about 3 times bigger than the solar system in diameter. If you count the outer solar system as being where Neptune is, it's colossal, and so that makes it an easier target as well. And that's why on the 10th of April 2019, I think it was, we saw that great announcement of the first image of the event horizon of a black hole. But what's now happened is that we've seen something that in many ways puts another piece in the jigsaw puzzle. M87 is known to be what we call an active galaxy, which means it is its black hole, its supermassive black hole, is essentially gobbling up stuff around it very voraciously and squirting it back out again as these 2 jets perpendicular to the disk of material, the accretion disk. So that's what makes it active. It's relatively quiescent at the moment, and so that was another reason why it was thought to be a good time to look at it. But the mechanism for a swirling disk of material to turn into jets going up and down from a black hole is thought to be strong magnetic fields, that it's all, apparently the magnetic fields have got more of a pull than the black hole itself, which sounds a bit comical, but because the magnetic fields are generated by the black hole. And what the scientists have now done is analyze the polarization of the signal that's coming from that bright ring around the event horizon, that kind of donut. And polarization, we're all familiar with it from polarizing sunglasses, but it actually, in astronomy, when you can study the polarization, it tells you about the magnetic fields that are present. Partly because it does things like magnetic fields align dust particles, and the alignment of dust particles is something you can measure with polarization. So they've done that, and what we're seeing now is the result. It was released last week, I think Wednesday, late Wednesday night our time, just too late for my ABC radio broadcast, which is always a pain. Anyway, the image shows. Essentially, they've depicted the way the magnetic fields actually spiral around the event horizon, and that kind of fits the puzzle of how these jets of material come out. The amazing thing, Andrew, here's an amazing fact: these jets of material are 5,000 light years long. So they're not just, they're not little things that pop out the black hole and they're really nearby. So you don't need an Event Horizon telescope to see them. You can see them with any radio telescope pretty well. But they're generated by the forces from within the black hole. The forces are they're unbelievable, just unbelievable.
And it's just hard to fathom that kind of power.
Exactly.
The enormity of this thing, as you described at the beginning, is hard enough to comprehend, but the awesome power within is it's beyond me.
It's beyond us all, really. I mean, sitting on that jet on the way to Adelaide when it took off, I thought, yeah, this is great. This is power personified, but it pales into insignificance next to what's going on in a black hole.
And this might seem like a dumb question, but, we're still unravelling the mysteries of black holes. We don't understand them. We're sort of piecing information together bit by bit to try and create the big picture, which will ultimately answer our question one day into the future. But what about magnetic fields? How well do we understand those?
Yeah, actually, probably better than anybody might pick up from our conversations, because we don't often talk about them, or we're going to talk about them again today in regard to planets. But the magnetic fields pervade the universe, and they have a very important role. Our galaxy has a magnetic field. Work that one out. 400 billion stars, 200 billion stars, or whatever it is. It's got its own magnetic field. And we know that they are important in many astrophysical processes. One of my former colleagues here, Brian Gensler, who now is in Canada, I think he runs the Hertzberg Institute in Canada, his speciality was cosmic magnetic fields. And you'd only got to talk to him for 5 minutes before you realise that the whole universe works on magnetism. And that is actually one of the questions that the Square Kilometre Array radio telescope is being built for. It's one of the fundamental questions that it will ask. This is the one in Western Australia and South Africa. How did the universe's magnetic fields come into being? What a great question. And I think, are you still there? What's happened to Google Chrome? Oh, it's trying to update it. No, it's all right. Sorry. Something funny happened to my... Yeah, you just vanished.
Don't you love? Look, you got to love the way these people who create these browsers and certain interfaces don't consider that people are actually working when they want to do the update. We have. I know it's a bit of sideline chat, but we have a computer at the radio station that we use when we haven't got live programs to air. So we run automated programs, but Windows will do an update in the middle of the night and knock us off the air. It's just, and you can't stop it.
No, I know. Well, this is fortunately nothing happened there. It didn't interrupt the thing. It just another window appeared, and this lovely face of Andrew Dunkley that was there suddenly was a blank screen.
But I've never heard that word used to describe my face before.
I'm not.
Dear.
Anyway, so the Square Kilometre Array, one of its quests is how did the universe get its magnetism? What a great thing to ask about.
I'm glad I brought it up.
I'm glad you did too, because we don't talk about it enough.
No, we don't.
Yeah, there's a lot to say.
As you said, one of our audience questions is about that very thing. So we'll get into that shortly. But for now, we're going to take a little bit of a breather on the Space Nuts podcast, episode 246. Thanks for joining us.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Hi, Andrew Dunkley here with Professor Fred Watson. This is Space Nuts, the podcast. And Fred, let's move on to our next topic. That of the exo-asteroid Borisov, which we have talked about a few times, and I think as recently as last week we had a bit of a chat about it. But now they've been sort of crunching the data that they gathered from this, which was a sort of an incidental or almost accidental finding, but they managed to get a lot of data and they're going through it, and now they seem to have picked up on some kind of echo.
Well, no, it's a metaphorical echo.
Echo, right.
The echo was from last week.
Yeah.
Sorry about that. I should choose my words more carefully.
Excuse
me, Andrew. But this is a really interesting story. So it's the first interstellar comet. So Borisov is definitely not an asteroid because unlike Oumuamua, which showed evidence that it was outgassing something because its orbit changed, but there was nothing visible, and that's what's led to this idea that it's a piece of the crust of an exo-Pluto, something like Pluto, but in another solar system, and the solid nitrogen has broken off, and that's what we're seeing, the interstellar cowpat. Borisov was known to be a comet from the first because it developed all the features that we see on comets from the solar system. It developed a coma. This is a cloud of gas, glowing gas around the nucleus, which is the flying iceberg part of the comet. So it developed that. It also developed a tail, which is, of course, excuse me, Andrew, I've got a frog in my throat here, probably an interstellar one. The tail comes from the solar wind, the wind of radiation and particles coming from the sun that essentially blows the tail out behind the comet in the anti-solar direction, the direction away from the sun. So it was known from the beginning to be a comet. And there was some pretty rapid analysis done on comet Borisov, because of course as soon as you see this glowing tail, you can clap a spectrograph on it and find out what elements are in there, what ions actually of elements and molecules are being given off by the comet. And there were some unusual things found in that. I can't remember the details, but there were some slightly unusual ratios of one molecule to another, compared with the ones that you find in the solar system. But they weren't unique. They weren't completely different from what we find in the solar system. And so that sort of reassured astronomers that they're on the right track. This thing is definitely from outside. It can't possibly belong to the solar system because of the orbit that it's in, charging through the solar system. But what we've seen now is new information. And this has come from principally, I think, the Very Large Telescope, part of the European Southern Observatory, which, as I'm always at pains to point out, Australian astronomers have a strategic partnership with, so we can use those telescopes. They have telescopes down in northern Chile. And some observations that were made, of course, the comet is now sort of way out. I can't remember where it is, but it's in the outer region of the outer planets. It's stopped out gassing, so it's very hard to observe. So these would have been observations that were made during 1919, 1920, when the comet was at its closest to the sun and was at its most active in the sense that it was giving out these plumes of gas. But using the Very Large Telescope, and in particular an instrument called FORS-2, which is a spectroscopic instrument, it has an additional string to its bow, though, which you might not be surprised to hear what it is. It can measure the polarization as well as the spectrum of the light that it's looking at. So there you are. We've talked about polarization in the first story. Here it comes again, because this polarimetric technique, as it's called, lets you look at the structure of dust that's coming off the comet, because as well as releasing gas, when a comet outgasses, there's all clouds of dust come out as well. And in fact, they develop two separate tails, a plasma tail and a dust tail. So you can look at the dust, and the polarization lets you, as I think I said a few minutes ago, it lets you look at the alignment of dust grains. And it turns out that these dust grains are aligned in such a way that the astronomers can deduce that this object has never flown near a star. So that's why it's been described as the most pristine comet ever found. It's venturing into the inner solar system is the first time that it's been near a star, and it's actually had these dust grains released. But there's enough of a polarimetric signal in the dust grains, and it's about alignment and things like that, to tell these astronomers that this is the first time it's done that. And that is really quite a big discovery. There is only one other comet, and you'll probably remember this because I do. It's back in the 1990s, I think 1998 or thereabouts. There was a comet called Hale-Bopp. And yes. Hale-Bopp was very bright. It was, I think it was the one that stretched halfway across the sky when it was at its brightest.
Yes, it was spectacular.
That's right. Now, Hale-Bopp had similar characteristics in the sense that it was a pristine comet, and in fact, it wasn't quite as pristine as Borisov. But what the astronomers are saying is that Hale-Bopp is the most similar comet to Borisov. And Hale-Bopp is thought to have made only one passage of the sun before we saw it, if I can put it that way. So it had not been affected by the solar wind and the solar radiation. And that's what they're saying about Comet Borisov. So it turns out that it was a pristine object. And by that, I mean its composition is very similar to the cloud of gas and dust that it formed from. This is the blob of gas and dust that the whole solar system formed from. Comets are formed in the outer regions of that, and it's got essentially it's completely unaffected by starlight or star radiation, and then the comets fall into the inner solar system. That's how we're the familiarity that we have with them. But Hale-Bopp is thought to have only done that once. and Borisov now is thought to have never done it. So this was the first time it had passed anywhere near a star.
Until it came into our part of the world, and we gave it a bit of a dust up. So it's hightailing it out of here in a hurry.
Hang on, I'll write that down. That's really good, that one. I like that. Yeah.
Now, you said it's in the outer reaches of the solar system now. That must mean it is absolutely hurtling along if it's gone that far that fast.
I'm sorry I can't give you exact details of that, but yes, that's the thing. It is very high speed, and I guess by that I'm talking about 20-30 kilometres per second, perhaps even more than that, relative to the sun. It's sort of comparable with the speed of New Horizons, which was one of the fastest spacecraft ever launched. So yes, it's on its way, disappearing.
Now, it will never come back, will it? Unless it gets captured it won't. Somehow. No, it will hurtle off somewhere else.
Yeah. So the technical details are it's in what's called a hyperbolic orbit. So remember that the planets move in elliptical orbits because they're closed. They're orbits that go around the sun. Comets are usually in what are called parabolic orbits, which means it's like an ellipse but infinitely long. And that's because the cloud where they come from is so far away that the ellipse is a very, very long one, and it looks like a parabola. But then the next step, this is in the series of conic sections that you learn in mathematics, the next one is a hyperbola, which is a very open path because it's going so fast, it just sideswipes the sun, and then it's slightly deflected rather than being brought back in an ellipse. That's how you know it's interstellar.
Yeah, fantastic. And unlike our localized comets, which generally come and go, but the time spans are still quite massive.
Yeah, so that's right. Yeah. Some comets orbit in hundreds of thousands of years.
Yeah.
In fact, I think talking of bright comets, I think Comet McNaught, which was fabulous in our evening skies in 2007. I think that's got a period of about 100,000 years, which means poor old Rob McNaught, who I saw only a fortnight ago, he's got to wait a long time before his comet comes back.
Yeah. Well, he could just watch reruns of Days of Our Lives, and he still probably would. He probably wouldn't have to watch that twice to catch up. So
I'm not that sure that he's so engaged with things like that. You never know.
Oh dear, I find those shows so frustrating.
I don't think I've ever seen one, Andrew. So.
No, definitely not. There we are. More news on Borisov, and I'm guessing that as they keep crunching data, we'll find out even more, and we'll let you know once we have learned it ourselves. This is the Space Nuts podcast with Andrew Dunkley and Professor Fred Watson.
Space Nuts.
Welcome back. Thanks for joining us on the Space Nuts podcast, episode 246 with Andrew Dunkley and Fred Watson. And thank you to our patrons who have been financially supporting the podcast, many of them for quite a while. Your support is appreciated. We are aiming to get the podcast to a point where it's fully supported by the audience, and that means obviously we need to get more patrons. Now, if you would like to sign up as a patron, go to the Space Nuts podcast website, spacenutspodcast.com by coincidence, and click on the support button up in the top right hand corner, and all your options are there on how you can, if you'd wish, financially support the podcast. It starts at I think at $4.50 a month, but there are different packages available under whatever circumstances suit you. And yeah, look into it. You don't have to do it, but it's an option if you would like to become a patron and a financial supporter of the Space Nuts podcast. Keeps the lights on. See the light there? See how we did that? Anyway, we appreciate the support of our patrons, and we're looking for more and more ways to value add to the podcast through our patrons. So we'll be telling you about those sorts of things in the not too distant future. Hugh and I have been discussing some ideas, and I like a couple of them very much. The word adequate came up. Not going to tell you any more about that just yet, but Wait for the T-shirt. Anyway, that's where we're at. And thank you again if you're a supporter of the Space Nuts podcast through Patreon or Acast or Supercast or whatever platform you choose. Now, Fred, we're going to take some audience questions, and first up, we're off to the land of the long white cloud in New Zealand.
Hi, it's Christine from Dunedin, New Zealand. I'm just wondering how many planets actually have magnetic north and south like Earth, and how important is it that an Earth-like planet also have a magnetic north and south pole? Really love your podcast. Discovered them last year and use them whenever I drove to work, which is half hour either way. Thanks, guys.
Thank you, Christine. Love the accent. And thank you for listening. And obviously, Christine hasn't been listening long enough for those New Zealand jibes that I threw in some time ago. So I'm kind of glad I haven't done that lately. But it's all in good humour, Christine, I promise you. No, I do have a soft spot for the Kiwis, of course, being someone who's got a very strong interest in the First World War. Everyone knows about the Anzacs, and because we combined with the New Zealand soldiers to become the Anzacs, the Australian and New Zealand Army Corps, and fought together in World War One. And yeah, I do have a very strong feeling about that connectivity between our two nations, even though on the sporting field we hate each other. But we've got more in common than most other countries that neighbour each other have.
Absolutely.
So, it's very, very special.
It is a really special relationship, which I love.
It is, yeah. Now, Christine's question is, do other planets have magnetic poles? Now, we've been talking about magnetism a fair bit today, and it's a really good question, and I've never even thought about it before.
And the answer is yes. Well, let's just think about the solar system. The planets that have that don't have magnetic fields are outnumbered by the ones that do. So all the gas giants have got really strong magnetic fields. Mars doesn't. We do on Earth. Mercury does have a surprisingly strong magnetic field, given how small a planet it is. And that actually, Mercury is a really interesting case in point, because it also has, and we know this from, you can measure these things from the orbits of spacecraft around planets. We know it's got a big iron core, a much bigger iron core than you'd expect. And so one of the reasons why we think Mercury is like it is that at some time in its early history it was smashed into by something else that broke away most of the mantle, the region outside the core. Otherwise it would have been as big as the Earth and Venus.
Is that right?
But yeah, so it's thought to have been smashed up a bit. So what you've got is a planet with a thin mantle, relatively thin mantle, and a big stonking iron core in the middle. And the iron core is, of course, the secret of magnetic fields. If you've got something metallic, something ferrous, in fact, with iron, and iron is the most common metal throughout the universe, that is going to give you magnetism. And so it's actually likely that far more planets have magnetic north and south poles like the Earth does than the ones that don't. The ones that don't are probably relatively few and far between. And so Christine's other question is, how important is that? Well, in our case, it is very important, because it's the magnetic field that shields the Earth from the radiation of the sun, the magnetic particles that could be very harmful, their radiation, and that's not something you want. With our magnetism, those magnetic particles are sort of shifted away, so they're not bombarding us all the time, as they would, for example, on Mars. That's one of the hazards of humans going to Mars, because it is unlike the Earth in that it doesn't have a strong magnetic field. So, does an Earth-like planet have a magnetic north and south pole? Yes, because if it's Earth-like, it will have an iron core, the same as ours, and will get these magnetic poles. So a great question. And, it's one of the things that in many ways we are yet to discover about the exoplanets. We now know of more than 4,000 exoplanets orbiting other stars.
Yeah.
If you have enough information on them, and some of the observations that we can make do give us this information, then you can get the density of the planet, and that then tells you whether it's a rocky planet or a gas planet. So you've already got hints from that there might be magnetism out there. In fact, the gas planets have magnetic fields as well. As I said, the magnetic field around Jupiter is by far the strongest in the solar system. So very common. Yeah, seems likely that there's always going to be magnetic fields out there.
Well, so are they generated by different sources? You talked about Earth and the iron core, and Mercury, the iron core. Is that what generates our magnetic field? And if that's the case, what's generating it out? What's generating the magnetic field that encompasses our whole galaxy?
Yeah, that's right. So it is the iron cores that generate. It's what's called the dynamo effect. It's basically what goes on in a dynamo. Dynamos generate currents. Those currents probably flow through the core. Electrical currents flow through the core of the Earth and generate the magnetic field. It's the physics is pretty well understood. I'm not an expert on that, but I get the general drift of it. But for something like the galaxy's magnetic field, that's a really interesting question. Does it come from the aggregate of all the individual magnetic fields of the stars? And by the way, the sun has a really strong magnetic field as well, and that's what drives the activity in the sun. You probably realise that this is the magnetic edition of Space Nuts, episode 246. Yes. I think we've talked about it in every story so far.
This is how we suck you in. That's what it is.
It's just magnetic. But the universe itself, that could be something different, and that's what the astronomers who will be using the square kilometre array down the track to look at the magnetic field of the universe to try and work out how it originated, whether it is still all about dynamo effects, or whether there's some more fundamental underlying mechanism within the early universe.
And is it a highly variable thing? Because Australians would be well aware that we have an island called Magnetic Island, because the magnetism there is more significant than it is in other places. So why would that be? Is that because of the geology?
Yeah, I think so. I think in the case of Magnetic Island, and forgive me, this is as much an assumption as but I think it's because of high iron content. In a lot of hematite probably in the rocks. I'll check that, but yes. So the geology does affect, certainly on the Earth. It has an effect, but it is a variable thing, as you know, because the pole at the moment, the North Magnetic Pole, is whizzing across Siberia, on its way towards Siberia. So it's something that changes. And you can see why that would be, given the structure of the Earth. We talk about the core, the inner core, which is solid, and the outer core, which is liquid. Those are the iron cores, and then there's a mantle on top. We've got this lovely picture of it. But when you look at the natural landscape around it and see how much variation there is in it, just looking, I can look out to hills here at Terry Hills, as you might guess, and you see the way the topography varies. So the topography of the mantle and the core are going to vary. There'll be blobs of high density, blobs of low density, and if all that's sloshing around inside, then you're going to get variations in the magnetic field as well.
Indeed. There you go, Christine. Yes, was the answer to your question.
Definitely.
And thank you for sending a voice question in to us. Let's move on to our next inquisitor.
Hello, Andrew and Fred. My name is Åke and I'm from Sweden. A couple of nights ago, I captured an image of M51, the Whirlpool galaxy, through my telescope. Due to the distance to the galaxy, approximately 25 million light years, not so many photons per time unit hit my camera sensor, so I had to collect about 8 hours of data to get a decent final image. So my first question is, how many photons per time unit would you say hit my camera sensor, which is about 2.5 square centimeters? And the second question is, after traveling 25 million years through space, how is it even possible that the photons don't diffuse and make my image blurry? Thanks for a great show. I've enjoyed all 243 episodes so far.
Thank you, okay. Very, very good to hear from you again. And I think you mentioned there were pretty technical questions when we were talking about them earlier, Fred. Photons per time unit and diffusion of photons over vast distances. They're really fascinating questions, really.
What they are, and they go to the fundamentals of astronomical observations with telescopes. And I have to say that I used to have all these numbers at my fingertips when I was doing this sort of thing myself, but I've had to look things up because I've got a bit rusty on it. So photons are the subatomic particles that carry light and magnetism, of course, just to get magnetism into this as well. It's the electromagnetic subatomic particle. And yes, so from the, when we're looking in normal daylight or artificial light and seeing things that are going on, you are seeing absolutely gazillions of photons. But astronomers looking at very faint objects get interested in, the smaller numbers of photons. For many years, I used to use an instrument called the IPCS, which is an acronym for the Image Photon Counting System. This was in the 1980s. And it actually was a machine that literally counted individual photons and formed an image with them. And the things I was looking at very faint variable stars in the center of our galaxy. And you could kind of almost see the photons coming in one by one as it built up the image. And I remember having signals that were barely there. It was a tough gig actually to extract information from them. So astronomers deal in photons kind of by the handful, which is what Åke's getting at, I think. I didn't do the calculation for him, and there are so many variables here. A galaxy, and the Whirlpool galaxy is a beautiful galaxy, and I'm sure Åke's image is stunning. But galaxies are, they've got what we call a surface brightness, the number of magnitudes per square arc second. Magnitudes are the scale that we use to measure brightness. And the surface brightness of galaxies is relatively low. It's not that high. And so that's why it takes 8 hours to form an image, because you're just getting bundles of photons from each arc second. What I'm going to do is just, for Åke's benefit, there is a lot on the web that you can discover about this. And there is a really pretty technical page that's aimed at professional astronomers. It's on the Harvard University website. It's actually CFA, which is the Center for Astrophysics. So that's web.cfa.harvard.edu. I won't give you the full reference, but I noticed that the two names attached to this HTML are Fabricant and Huchra, Dan Fabricant and John Huchra, two very, very big names in the world of astronomy. But it's a website called Astronomical Magnitude Systems, and it goes through the whole definition of how we define this scale of brightness that we use. But there is a section which is called photon flux, and it is quite complicated, and you've got to spend a bit of time to figure out what's going on, because it converts magnitudes via Janskis, which are a unit that are more often used in radio astronomy, but they're a flux unit. And you can end up by working out how many photons you're receiving. And let me just give you one example, which is how many what are called V-band photons. Now, these are photons in the visible band of the spectrum. So rather than the blue or red region, it's the greenish region of the spectrum. How many V-band photons are incident per second on an area of 1 square meter? at the top of the atmosphere. In other words, you're neglecting the atmosphere from this, from a V equals 23.90 star. Now, that is a very, very faint star, 23rd magnitude. It's nearly 24th magnitude, is at the limits of observability for a big telescope, for a 4-meter telescope. You're talking now, though, about a 1-meter telescope. You've got a 1 square meter aperture. That's the diameter, the collecting area of the telescope. And the answer is 2.42 photons per second. So, you're talking tiny, tiny numbers. This is a faint object, but they are still there. You can count them, if you've got photon counting devices. It's a really interesting topic. I won't go into any more detail, but Orca, check it out on the web. There's a few websites where people discuss this kind of thing, and you will find, you will get some idea of how many photons was coming to you, to your camera sensor when you took your image of the Whirlpool galaxy. And Orca's other question,
why they don't diffuse?
Why they don't diffuse? That's right. Yeah. So, and that's because in the vacuum of space, there's nothing to diffuse them. Essentially, these streams of photons. So, what you've got, if you imagine the galaxy itself, this beautiful-looking object, every part of that galaxy is squirting photons out, and they travel. They travel in all directions, but each one only goes in one direction, and that's the one that you pick up in your telescope if it's pointing the right way. And they don't start diffusing until they hit the Earth's atmosphere, and that's the problem with the atmosphere. They do exactly what Orca's talking about over the last 10 kilometres of their journey. They travel for 25 million years with no diffusion whatsoever, hit the atmosphere, and then all bets are off. If you've unless you've got really good atmospheric conditions, which is why you build telescopes on mountaintops. So they're great questions, and it's good to think about things in the photon regime, because that's really what professional astronomers are focused on, if I can put it that way.
Yes, indeed. And we've talked about the subatomic particles and their various roles before, and that's one of the great mysteries they're trying to unravel, whether or not there's some kind of subatomic particle that carries some of the more mysterious things that we're trying to learn about, like dark energy, dark matter, who knows what else is out there that we haven't yet discovered, as we mentioned last week, that again could be attributable to yet to be discovered subatomic particles. So it's a fascinating world. I'm pretty sure they'll unravel it one day, though, Fred. I'm very confident that we learn so much so fast these days. It's only a matter of time before someone has a brainwave idea and goes, "Oh, I might go and check the." Oh, that's what dark matter is. It's dry peanut butter. That's what it is.
Oh, there you go. Oh, look, you might have something there, Andrew. I'd
no.
Check that out.
Could be. All right. Thanks again for your questions today. Really appreciate it. And, of course, if you do want to send us an audio question, you can do that via our website, spacenutspodcast.com, and click on the AMA link. And you can record your question there, or you can send it as a text question via our email interface. Now, we do have a whole bunch of text questions that have been sent to us, but they were compiled on a spreadsheet that we can't read because for some reason it's formatted itself into one line. So the question is, "Hi, Andrew and Fred, really love the and the rest of it's over there."
Yes, next door.
So we haven't figured out yet how to decipher that. So if you have sent us text questions, we haven't ignored them. We just can't read more than the "Hello, I'm Sarah and I'm from Santan," and that's about it, or whatever. But we'll try and get to them because you certainly deserve a hearing as much as anybody else. So leave that one with us. We'll get back to you in a light second or two. Maybe longer. But anyway, thanks again for your support of the Space Nuts podcast. I think that brings us to an end. Something I haven't mentioned for a long time is the Space Nuts shop on our on our website. While you're looking at recording your question, just click on the shop button as well and have a look at our vast array of product, our T-shirts, our polo shirts, our mugs, our caps, our cups. You might like to get yourself something special as a Space Nuts listener. You could wear that proudly down the street. What the hell's a Space Nut, mate? Well, it's a new form of pistachio, if you should know. But anyway, we'll leave it there. Thank you, Fred, as always. Great to talk to you.
Good to talk to you, Andrew, as well. And keep up the good work. I think we explore many different aspects of the universe, from pistachios to magnetic fields. We do it all. Indeed,
yes. Look, I wouldn't think there'd be too many other podcasts that combine those two things into the one subject matter.
Yeah.
All right, Fred. Nice to see you. Talk to you
soon. Later. Take care. Bye for now.
Professor Fred Watson, astronomer at large, part of the team here, the vast team of three that put together the Space Nuts podcast. Hello to Hugh in the studio. And from me, Andrew Dunkley, thanks again. We'll talk to you again next week. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast. Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.